Dear participants, my name is Olha Bohomaz. I am pleased to present my report on the topic Physical and Mechanical Properties of Burnout Coal Mine Waste Heaps. One of the most important environmental issues in the mining industry is the problem of managing soil waste from the mining industry. According to statistical data, before the start of full-scale Russian-Ukrainian war, there was a tendency in Ukraine to increase the volumes of solid waste generated at mining industry enterprises. Over the last almost 2 years, the volume of solid waste generated has probably decreased due to a reduction in the number of coal mining enterprises operated in the Donetsk and Lugansk region. The low level of utilization and recycling of waste rock results in its significant accumulation on the daily surface in the form of waste rock dumps. Over the past 50 years, over 25 billion tons of mining waste have been accumulated in the coal mine region of Ukraine, occupying thousands of hectares of fertile land. Therefore, the issue of finding new ways to process, utilize, and reuse burn-out waste heaps in order to reduce their technogen impact on the environment becomes relevant. The presence of a porous structure in combination with undissolved properties opens up the possibility of using both burnout and common mine rocks to make composite fertilizers to improve the quality of agriculture degraded soil. To do this, the rock is mixed with an organic component, which can be municipal sewage sludge or water body silt. Studies have shown that the addition of coal industry waste and its mixtures with municipal sewage sludge and rock wool waste improve soil pH and its occlusion properties. Laboratory studies have confirmed that the creation of a nutrition mixture based on 25 burnout mine rock, 25% river silt, and 50% degraded loamy black soil treated with red California worms allow for 100% germinate of plants. Unlike other substrates that did not contain burnout rock. However, the widespread use of burnout mine rock for the manufacture of composite soil requires the study of their physical and chemical properties and deformation characteristics. The purpose of this paper is to evaluate the effect of particle size distribution on the physical and mechanical properties of the burnout waste rock. Samples for the study of rock properties were taken from the non-operational heap of mine number 5-6 of the Mirnograd Vugilya. The largest of the selected pieces were crushed mechanically. After crushing the rock, the resulting particles were separated using laboratory sieves into three fractions. First fraction from 10 to 5, second fraction from 5 to 3, and third fraction from 3 to 1.25 millimeters. To determine the deformation characteristics of the rock in each fraction, 4 samples were prepared. A reference without additives and 3 samples each with the additional of loamy soil typical for this area with a mass concentration of 10, 20 or 30 and 30%. On the first step of research, each rock fraction was microscopically examined using a monocular microscope. From the results, it follows that particles with a size of 10 to 3 millimeters are characterized by a flat shape. There are pores, there are no cracks, and there are stepwise folds. Smaller particles are characterized by a round shape, greater porosity, and a higher frequency of cracks and folds. Unlike others, the 5-3 mm fraction is characterized by sharp edges which may affect the nature of the deformation process. In the large fraction, the presence of sharp protrusions is less pronounced. The deformation characteristic were determined using a press P50, which photos are presented on the slide. According to the results of first test, it was found that there is a parabolic relationship between the energy expended on the compression of the rock sample and its deformation. It's valid for all types of the tested samples. At the beginning of loading, deformation occurs at a high rate. The addition of soil to the fraction did not significantly affect the determination pattern of the samples. For almost all tested samples, the final deformation was about 0.02–0.025 meters at a loading energy of 250 joule. The results obtained revealed a certain increase in load resistance when soil powder was added during the initial compressing period. Almost all the lines of the graph characterized the power required for compression located above the line and characteristic of pure rock. This can be explained by the contact stress leaving effect due to the filling of voids with powder and therefore an increase in the interaction areas of rock particles. The destruction of rock particles was observed in most cases at a pressure of 1,500–1,800 kilopascal, which is typical for burn-out milestones. After crushing such particles, their mutual sliding occurred with a slight decrease in the power required for future deformation. The next wave of particle crushing was observed when the pressure increased to an index approximately equal to 3,800–4,000 kilopascal, which is typical for siltstones and sandstones. Subsequent to rate of pressure growth slowed down. After the active destruction of rock particles was completed, the material consolidated and deformation of the samples occurred at almost the same rate. These results indicate the presence of two strange limits in the burnout medium composite of two initial petrotypes. Conclusions. The methodology of the experiment did not provide for the registration of the process of rock breaking. Only its results were reported. In the future, it will be advisable to observe mechanical and acoustic phenomena in the samples in parallel with the compression of the samples to clarify the period of intense rock destruction. The data obtained will use in the future to reveal the mechanism of deformation of a mixture of rock with wet bottom sediments. To assess the impact of the deformation of a mixture of rock and wet sediments, it's necessary to consider the possibility of air in the porous cracks and gaps between the particles. That's all. Thank you for your attention.